Welcome to the second plenary talk of this 2022 European Control Conference. And it's my great pleasure and honor to introduce Professor Marios Polycarpou. Well, I was thinking I could deliver a plenary lecture just to explain the whole kind of activities, awards, and so on, but I will be brief, so not to grab too much space from this talk. So Marios is a professor of electrical and computer engineering and the director of the KIOS Center of Research and Innovation at University of Cyprus. And Marios is also a member of the Cyprus Academy of Science, Letters and Art. And also, last but not least, he's an honorary professor at the Imperial College London. Marios got his PhD in 1992 from University of Cedar, California. And I should not tell how many papers, books, and patents and everything Marios published. I will start to say that actually today or yesterday, it was announced that Marios actually was, please get in, got the 2023 Frank Rosenblatt Technical Field Award from IEEE. This is the major award, the best award that a scientist could get in computational intelligence, neural network, and these kind of topics. Marios also received the 2016 IEEE Neural Networks Pioneers Award. He's a fellow of the IEEE and of the IFAC, and he also is the recipient of the 2014 Best Paper Award for the Journal on Building and Environment. He was the president of the IEEE Computational Intelligence Society. By the way, he was the president of the European Control Association, which for us is, of course, very important. He was the editor-in-chief of the IEEE Transactional Neural Networks and Learning System, and he is currently on the editorial board of the proceedings of the IEEE. And coming to the research excellence, Marios was awarded the ERC Advanced Grant and the ERC Synergy Grant, which is the most prestigious grant you can get in Europe, and it's the first for Cyprus. And of course, also, he has been awarded of the EU Teaming Project, which is a flagship project. So I think I will stop talking about your many awards, Marios, and I welcome to deliver this exciting talk.
Thank you, Thomas.
You don't have that? Okay, you can take this one. Take this one.
I always wanted to wear one of these. So good morning, everybody. It's a great pleasure to be here. I was one of the people that organized the ECC 4 years ago in Cyprus. So it's ECC has a special conference for me. I would also like to thank the organizers for the invitation. It's a great honor to be here and to talk about this topic. So typically, a lot of the presentations that I make are more theoretical, more equations. Today, I'm going to focus a little bit on an application. This is an application that I think is important. And moreover, I think it's becoming even more important. And I think the system and controls community have something to contribute. And I hope that you will see by the end of the presentation that this is the case. This is work that I'm doing with several colleagues and PhD students, but I would like to mention specifically Dimitris Iliadis and Stelios Vrahimis that are integral part of the results that I will be presenting. Okay, let's see. Is it? Can I get some help? Okay. So why is water important? It's somebody might say, I just turn on the water tap, there's water coming. Why is it so important? Of course, the same thing can be said about electricity. In the case of water, it's important to note that in fact we are quite lucky, a lot of us, to have not to worry about it. Recently, one of the articles in Nature actually indicated that there's 80% of the world population is exposed to high level of water, to threat of water security, especially due to anthropogenic climate changes. So some people don't have enough water, other people don't, the water is not of good enough quality. But there's a big part of the world population that is actually influenced in a significant way. And this is estimated to increase in the future because more and more people, well, the population is increasing. And in addition, a lot of the world population wants to live in big cities. So that puts a lot of pressure on water resources. It is estimated that by the year 2050, we're going to have 70% of the world population in urban areas, which is an issue. So this urbanization can cause significant increase in water demand. Now, if we look at it from a systems perspective, urban water distribution systems are complex, large-scale, time-varying, and long-lasting networks. What do I mean by long-lasting? Once we do something, once we dig and put some infrastructure there, we cannot say, oops, I made a mistake, then let me change some things. So this is something, so it's a system that is complex, and but so far there's little system and controls tools that have been applied to a large extent, because it has been operating in a kind of an open loop with not a lot of sensors. And this is about to change. And I think the role of system and controls is becoming more and more important. So this presentation is to talk about the role of system and control in the water systems, and specifically in urban water networks. Now, with the climate change, this is something that was already a water resource was already limited, is becoming even more precious, and this is going to continue in the future. And I list here a couple of examples of problems in Italy and in Bolivia, but there's a lot of problems worldwide. So the message is that water is precious, and it's going to become even more precious in the future. Now, what can we do as systems and controls people? Where can we contribute? Of course, we cannot solve the climate change problem, but we can contribute in some key challenges of water distribution systems, and I'm listing here four of these, which I think are very important, and I think that we can contribute significantly in these areas. One is there's 25% of the water that is actually being produced in Europe is lost because of leakages and theft and so things like that. So this is something that we can do better, and I'll talk more about it. The other thing is about the quality of the water. There's new directives that are coming out. There's new studies that indicate the quality of water is not at the required level, and we need to do more about it. And again, this is an area that system and controls people can contribute. The other thing that is important, and a lot of people don't realize that, is actually 4% of the electricity that we produce is actually used for moving water. So the water utilities actually utilize 4% of the whole electricity that is produced. That's a huge amount, and I think there's even if we improve that by 10%, that's going to be a significant change. And finally, with the new sensors, with the new instrumentation that is going on, the safety and security of water systems is becoming very important. So let's go through these 4 areas and talk a little bit about what is the challenge. So this shows the issue with water loss. 25% of the water in Europe is lost. In some cities worldwide, this is a lot larger. So I'm showing some of the cities with the largest percentage of non-revenue water. So what is the cause of this? There's aging infrastructure, there's pipe breaks, there's background leakages, tank overflows, water theft, and metering errors. So overall, just to get an idea, just to get an image is drinking water losses daily, every day, it's equivalent to 46,000 Olympic pools. So this is a lot of water that is lost every day. This is water that has already been cleaned and is lost. And so you may think, what can we do? If a pipe breaks, the water is lost. However, a lot of the losses are actually not like that, because the big losses are easy to detect and take care of quickly. A lot of the ones that actually accumulate to be very big are small losses that are never detected. So a small amount of water is lost for a very long time, and that's a big part of the problem. So this is with regard to water losses. When it comes to water quality, the raw water is usually dirty, is cleaned, disinfected, and then is sent to the consumers. So the way that the water is disinfected is usually with chlorination. So this is one of the it's not always. Some countries use some other techniques, but most of the countries use chlorination. Now, with chlorination, there's the issue of how much chlorine do you put. If you put enough chlorine to kill all the bacteria, then you may get problems with taste, with smell, with complaints. But this is not the biggest problem. The biggest problem is that some studies show that these chlorination byproducts are actually carcinogenic. So you want to put enough chlorine to be able to kill the pathogens in the water. Okay, and of course the way that the disinfectant decays over time. At the same time, you don't want to put too much. So there's definitely a control problem to be solved there. So in addition to that, then you have contamination events due to managing accidental or other contamination events, as well as malicious attacks that might contaminate the water. So water quality is another key issue, and one example that indicates that this was an accidental contamination crisis that happened in Nokia. Nokia is among other things, is a city in Finland where there was a 2-day delay to detect a contamination, an accidental contamination that caused 10,000 people to be affected and 3 months of water ban. Now, if there was some algorithm that could detect this immediately or in 5 or 1 hour, that would have solved these problems. The other issue is with regards to energy consumption. As I mentioned, 4% of the EU electricity is used by the water industry. This is for moving water. And this is not only in Europe, this is for pumping. This is also in the US. And of course, this can result in significant greenhouse gas emission. For those that are keeping track, there's just for moving water in the UK, and UK doesn't have a lot of mountains and things like that, but still 4 million tons of CO2 equivalent are used just for moving water, and in the US that's actually 10 times more. So there is potential for significant savings, even if we can do something about that. And finally, safety and security. In the case, this is something that water utilities didn't have to worry about. Nobody cared about it before because everything was manual. Now, with more automation, there are more the potential of malicious attack. And this was illustrated last year when there was an attack by a hacker in Florida, which actually modified the chemical concentration of a certain chemical by 100 times. Luckily, nothing happened because one of the operators actually noticed something, but if it wasn't noticed manually, it would have created a significant problem. So, the trend nowadays is towards having more instrumentation. So I started, personally, I started working in water systems in 1995. So that's more than 25 years ago. And at that time, I had a master's student that wanted to work on something of environmental issue. And we found a group in the environmental engineering department that we could contribute to, but at that time there was not much sensing going on. Everything was open loop. So most of the work that actually we did at that time was just in the modeling and trying to understand on how systems people can contribute. Now there's more and more advanced technologies that are being developed. And the idea, but we're still not there. So this is the goal is to use these technologies to enhance the efficiency, security, reliability, and to minimize the effect of unforeseen events. So this picture that we're all familiar with is just used to illustrate that for a long time, a water system was actually just the water system, and with very few sensors, very few actuators, no closed loop control. So all these are new to the water community, and this is what I want to talk about. And so when we talk about water system, what are we talking about? I mean, what are the things that a water system is about? There are two types of dynamics that are very important in water system. One is the hydraulic dynamics, and the other one is the water quality dynamics. There's others that can be taken into consideration, but most of the work out there is in these two areas. So the hydraulic dynamics, the hydraulic states estimate the water flows and pressures, while the water quality dynamics is usually some chemical concentration. So usually civil engineers deal mostly with hydraulic dynamics, environmental engineers, and some chemical engineers deal mostly with water quality dynamics. Usually computer engineers and electrical engineers don't have a key role. And this is where we come in nowadays with the new technologies that are being developed in order to be able to do things like real-time control and optimization. So if we could do this, if we can estimate the states, then we can do some of the techniques that we know about in order to detect pipe breaks, equipment failure, water contamination, cyber attacks, and so on. Unfortunately, real-time estimation in the current setting is not something that is is used in practice. And let me explain why, what is the current practice, and see where things are going and where we could contribute. So in terms of hydraulics, what we have is similar to energy and power systems. What we have is we have a transmission network and a distribution network. So the transmission network is usually the big pipes, and the distribution network is in the cities. And usually, water comes from reservoirs or from other sources, is cleaned and pumped to where it wants to go. So the hydraulic states are, described by pressures at nodes, tank levels, flows in the links, and so on. What is an important thing that is uncertain and creates a lot of the research motivation for some of the things that are coming later on is that the water demands are actually an uncontrolled input. So what we have is we have water demands that we don't know. We have some aggregate estimates, but we cannot use that to estimate, what are the flows in the different links and so on. Now, the actuators, in terms of hydraulics, are usually valves and pumps, but they are very not advanced control algorithms. And a lot of them are actually open loop, manually operated. So the distribution network is usually separated into what is called district meter areas, and in the current practice, all they have a lot of times is just they have some pressure and flow meter entering a district and DMA. That's what it's called, and that's all there is. And you can think that it's very hard to do control just with one sensor in a network that has so many nodes. Now, what is envisioned, and this is where the technology is heading, is to have remote sensing, a lot more real-time state estimation using measurements, remote actuation for real-time pressure and flow control, and that's why the people from our communities can actually contribute in these areas. In the water quality, it's actually even worse because there's hardly any sensors. The water disinfectant, which is usually chlorine, is injected only at one location where after the water is cleaned, usually in an open loop fashion. They just have a schedule that, and then what they do is that somebody goes to different parts of the network, maybe once a day or maybe once every 3 days, gets some sample of water, takes it to the lab. Usually takes 24 hours to analyze what is in the water, and this is all just to make sure, so you can see if there was a contamination to happen, that would be a disaster because it wouldn't be caught early on. So what is envisioned here, and already there's a lot of sensing that is being developed, is multi-parameter sensors placed for quality monitoring and contaminant detection. Disinfection booster stations for improved regulation. So instead of having one input, one control input, to have several booster stations at different locations based on real feedback information in order to do that. So this is what is envisioned, but is not in practice yet for many reasons. But this is actually something that is actually starting to happen. So in summary, if we were to look at from a controls viewpoint, what we have is we have two types of dynamics, the hydraulic dynamics and the water quality dynamics. The hydraulic dynamics, because of the flows, affect the water quality dynamics. The disinfectant chlorination, if the water is not moving, then there's a decay in the disinfectant over time, so it's not as effective. Well, if the water is moving fast, so the disinfectant is moving with the water. So so the flows, the hydraulic dynamics affect the water quality dynamics, but not vice versa. So this is the general setting. And in the last few years, there's been work in these areas. I just wanted to mention some of the things that have been done, especially from other people in this area, especially and also from our community. Some in the hydraulics area, there's been work on sensor placement, demand estimation, state estimation, leakage diagnosis, demand management. In the area of water quality, there's been, again, where do you place these sensors? This is an important area because, you know, you may have 1,000 or 10,000 nodes, and you may have like 5, 10 sensors to install. It's not just the cost of the sensors. Unlike other applications where 90% of something is the cost of buying the sensor, in the case of water system, even when you buy the sensor, in order to install the sensor, usually requires significant cost, and also maintaining the sensor over time also requires significant cost. So this is an important thing. So some other areas that people have worked on is booster chlorination, valve control to mitigate contamination, which can be thought as a kind of a fault accommodation problem, and also modeling of contamination impact on society. So these are some of the areas that people have worked in, as well as in the area. So this water energy nexus is something that I know in the EU is becoming an important research area. And one of the reasons, as I said, there are several other reasons, but one of them is that a big percentage of the electricity of the energy in general is used for water movement. So there's an incentive to optimize water pump control under uncertainty, to optimize water pump selection for load shedding to reduce the risk of power system instability and water shortage. Also to detect anomalies in pump energy consumption in real time and so on. So this is another area that people have worked, and also finally in the area of cyber physical security and how to detect cyber physical attacks in the case of water systems as quickly as possible. So in the rest of my presentation, what I'm going to do is I'm going to talk about different aspects that are related to system and controls that with some results. I'm not going to be able to cover a lot of things, but you get an idea of some of the things that are going on and where the system and controls community can contribute. So there's modeling, decision, estimation, control, diagnosis, and developing research tools. And I'll talk a little bit about each one of these. So, so when we talk about the modeling of hydraulics, these are typically described by conservation of energy and conservation of mass at nodes. So these are nonlinear, they are not highly complicated. At the same time, What makes it complicated is that the network is actually large scale. So you may have 10,000 nodes, many more links so this is what makes it more challenging. And the fact that it's a system that is very, I mean, there's not enough sensors. So all the techniques that we learn in system of controls, for developing system, state estimation and so on, is not an observable system. So you cannot do. So this describes the flow and the head, which is basically the pressure as well as the dynamic states. So in terms of sensor placement, so there's sensor placement for hydraulics. Where do you put like flow sensors and pressure sensors in order to make the sensors most sensitive to leakages and to minimize estimation uncertainty? And there's also placing quality sensors for monitoring. So this is typically a multi-objective problem that you want to minimize the contamination impact. How do you minimize the contamination impact? You can think of the contamination impact as the amount of water that gets contaminated or the number of people that get impacted. Both have been used. You can think of it both ways, but also to minimize the detection delay. So if you have a network of 10,000 nodes and you have 5 sensors, you can develop methods, and we have all developed methods. I'm not going to go through the details of the methodologies in the interest of time, but I'm giving a lot of the references. But you can actually move, maybe just by moving the location of the sensors slightly, you can get much better. And this is usually the case. And this is not something even the experts, the experts in my experience have a little bit of a good intuition when it comes to hydraulics. When it comes to water quality, not so much. But if you ask them, they think they know where to place the sensors, to achieve the best results. But once you try and simulate their solution versus the optimal solution, it's not as good as they think it is. So they think they are better than what they are in practice. In the case of water quality, they don't have a lot of intuition at all, because it's hard to see how, if there's a contamination, how it's going to propagate, and if you have a limited number of sensors, where you want to place them. Now, when it comes to state estimation, one of the most popular simulation packages for modeling water distribution systems is called EPANet. And it's mostly used offline. And if you input the demands and the controls, you can find the flows and pressures based on that information. Of course, in practice, you don't know the demands, so that creates a lot of uncertainty. So a big part in hydraulic state estimation is to work with the uncertainty, and to be able, a lot of the times, you're interested not only to find the different states that you cannot measure, but to find uncertainty bounds, because those uncertainty bounds are the ones that will be used in order to be able to detect leakages or water contaminations and so on. So a big part, because the water demands are changing and are uncertain, and it's not only the water demands, there's also other components in the model that are uncertain. One of the key issues is how to deal with, so it's mostly interval state estimation rather than point state estimation. And in this area, we developed an iterative technique that is actually calculating this interval state estimation that we use, as well as other people are using, both for fault diagnosis and for contamination detection. So this describes the iterative hydraulic interval state estimation methodology. Is based on computing the bounds as you move on, and the fact that it's iterative allows you to solve the problem in reasonable time. So this is one of the, I'm not going to go through the details, but this is the main idea. And here you can see a comparison with the calculated state bounds. So these are different nodes. So if you take every different nodes in the network, and given that you have, let's say, 10 sensors and you have some models and some uncertainty bounds, you want to be able to find these bounds, lower and upper bounds, over time for all the different nodes. And you can, in order to see how to evaluate the method, you can compare, of course, with Monte Carlo simulations, which takes forever to do, but it shows that these are actually tight bounds, which is one of the risks that is going on. This has also been improved with some colleagues from Brazil and Italy using constrained zonotopes for uncertain, it should be constrained, for uncertain state estimation. And the benefits of these constrained zonotopes is the fact that you can actually capture the dependency between the state variables. Okay, so you can make the bounds tighter, which really helps when it comes to leakage detection and providing higher leakage detection rates. So now, when regarding estimating water quality system, this is another area that we have done significant work in terms of developing algorithms. Given that you have some sensors, can you estimate the water quality in terms of chlorine concentration at different areas? This is an area that is becoming more important over time. And the idea is to be, again, it's not just a matter of doing state estimation, but to actually find, given that some of the bounds on the decay rate or the water demands, so given some knowledge about that, how can you actually estimate the water quality at different nodes in the network? I'm giving the reference here. One of the things that we tried and it worked very well in practice is to be able to use parameter estimation for some of the water quality parameters, for example, the chlorine decay rate, which actually showed that the performance was significantly better using this online parameter estimation of the decay rate rather than not using it and taking the best estimate, especially when it's changing over time. So some of these adaptive techniques are working quite well. In the area of control, so remember, this is the setting that we are dealing with. So we have water quality dynamics and water hydraulic dynamics, and controlling the quality is based on trying to follow some desired chlorine concentration. Now, there are two ways that you can do that. You can try to control the pump and valve, or you can try to inject chlorine. Now, in practice, the pump and valve control is used only for the hydraulics, because if you try to control the flows in order to affect the quality, that may affect the supply of water. So none of the water people want to deal with that. So so in practice, what is being done is use chlorine injection. Now the problem is if you put chlorine at the beginning of the network, then by the time that the disinfectant gets to the periphery of the network, is decayed, so it's not high enough in order to keep the water clean with respect to pathogens. While on the other hand, the people that are close to where the disinfectant was injected will get the high levels of chlorine, which is not good for them either. So in order to have a spatial temporal a suitable spatial temporal distribution of the chlorine, you need to be able to put different boosters at different locations. So this is one of the areas that that we are working, as well as other people are working in, which is it's a very difficult problem. So one area that adaptive control has been used is taking advantage of the periodic of the periodicity of water demands. We know that water demands in the morning, they go up when people use a lot of water, then they go down, and then they go up again when people come home, and then during the late night, they go way down. So this is the usual periodicity. So if you take that into consideration, then you can use adaptive control to be able to estimate how you want to inject chlorine in order to take that into consideration. In the area of diagnostics, so this state estimation is very important in terms of being able to use to detect leakages, because it's just one extra step that if you have where the bounds should be, then in the case that they exceed the bounds, that's where there's the indication of leakage detection. The way that this is done now in practice is that the water utilities manually look at late at night, 3 o'clock in the morning or 4 o'clock in the morning, where they expect that not many people would be using water, in order to detect if there's some big leakages. So this is something that, so somebody goes in the morning, they look at the late night, and if which is a very easy way, if it's more than what it should be or what they think it should be, then they say, however, with this method, you can only detect the big leakages, not the small ones. So when we worked with them and tried some of these algorithms, they were really impressed that we could actually detect, small leakages that were actually accumulating over time. And this is one example of an application. It's a small network, but we were able to detect leakages that they couldn't detect otherwise. And so this technique was actually extended more recently to the case of not only detecting or leakage, but also to be able to localize where the leakage is. And of course, in order to be able to do that, you need to have smarter algorithms. You need to have, especially if you don't have a lot of sensors, which you don't in practice, you want to be able to use the model in a way that that achieves that. So this is one of the areas that we worked on recently. And another area is the area of active contamination. So if there is an indication that maybe there is a contamination. So what happens is that somebody calls and says, I think there might be contamination at this site, or maybe there's an indication. So the usual way is to send someone over there. Usually there's some delays unless they think it's a big issue, to take some water, take it to the lab. So this usually takes at least 24 hours. So in the case of the contamination, this is not a very effective way. So one of the things that we tried is to, let's say you have some sensors in the network that detect the amount of chlorine concentration or the amount of contaminant in the network. So the idea is that can you close some valves in order to be able to direct the water towards the sensor as quickly as possible. So in general, this may seem a little bit counterintuitive because you're kind of distributing the possibly contaminated water away from where it starts from. However, the optimization is such that, you know, if this is going to take longer than, let's say, 24 hours to get there, then, you know, the old way is the best way. But what we found is that you can actually do much better. So in this case, we closed 3 of the valves so as to force the possibly contaminated water to go to the sensor. And of course, you know, for a large network, you need to be able to do that in an effective way. In this case, the amount of water that was contaminated was actually significantly less than what, even though the water is distributed in some nodes, if you just didn't do anything, there would be a lot more water that would be contaminating over time. Okay. So yeah, Thomas told me, make sure you look this way, not this way, because that's where the clock is. So just 5 minutes and I'll be done. So this is the optimization problem that was set up in order to achieve this. So the 2 things that we want to do is minimize the contamination impact and also minimize the number of valve changes and so on. So in closing, I'd like to talk briefly about some of the test beds and tools, research tools that we are developing at the center where I'm at. For water security. So this is a water security test bed that allows us to actually, you know, none of the water utilities, we have a very good relationship with them, but none of them will allow us to play around with their network. You can imagine water is not something that you want to play with. And so this gives us a playground, and we can include cyber physical attacks, we can include leaks, we can do different things for research purposes, so it's a very nice system that was developed, and we also got data sets which is available online for people to use and play with. So this is something that we developed. Another thing that we developed is actually what is called the GEOS virtual city. So this is based on a real city in Cyprus using open data, what we did, we integrated realistic simulation. We have an integrated realistic simulation platform of most of the city infrastructure. So for security reasons, we changed some things, but everything is based on open data, and where we have, you know, in addition to the water, we also have the power network, we also have the transport network, and as well as the telecommunication network. So this can help to simulate interdependencies between the systems and actually to try different things and different algorithms. And of course, other researchers are welcome to utilize this as well. So this can simulate events in the city, for example, for malicious attacks or accidents or natural disasters and so on. So this is the GEOS virtual city. And also it I just wanted to mention, it's used for research and operator training. And this also helps to generate benchmarks and tools for the controls community. So one of the benchmarks that we develop is a competition, actually, in terms of, so we created a realistic we use a 2-year simulated SCADA data set with leakages in order to have a competition with leakage detection and isolation methods. And this is a competition that went on and there was a winner. In addition, we have a tool for developing algorithms for water systems using MATLAB. Most of the control engineers don't know how to use EPANet, which is what the water hydraulics people are using. So we developed this toolkit to convert things to MATLAB so somebody can work with MATLAB. And also some other databases, especially for using with machine learning algorithms. Finally, I just wanted to mention briefly the ERC Synergy grant that Thomas mentioned. This is something that started last year. It's just recently started, and it's in the area of water systems. And what it does, it brings together people from the water engineering community, people from, we have an environmental economist to talk about policy making and for water supply. And we also have a computer scientist for developing machine learning algorithms. So the main idea here is to look at it from a, as the system is evolving, how to optimize the design as well as the operation of this system. And in that light, we are working on looking into, this is the diagram that you saw earlier. Now, this is kind of, think of it as the low-level control, and we're looking into the outer layer in order to see what should be the objectives for this system. So this is my last slide. So I know that I'm the last obstacle between you and your lunch. So let me just try to finish up. What I want you to remember, if possible, is that water is a very precious resource, which is actually becoming even more precious. So if this is something that, you remember that when you drink some water or maybe when you have a shower, usually when you have a shower, you have a lot of time. So think about that. It's a very important quantity. It's a very important resource. And the other thing that is important is that the water distribution system is going through a digital transformation with new instrumentation and sensing and actuation. And actually the Internet of Things is going to affect things quite a bit. And system and control can play a key role in developing these intelligent algorithms and new tools for making water distribution systems more efficient, more resilient, more secure, and more aligned with the green economy. So I just wanted to acknowledge the support of the ERC, and also we have a teaming project in collaboration with Imperial that is supporting this work. And finally, last but not least, I should mention that we have a very long-term collaboration with the water utilities. So the Cyprus Water Development Department is the one that is responsible for the transmission of the water. And then each city is responsible and we have a long-term collaboration with the Water Board of Limassol as well as other cities, which is very important in order to do this work because they know how the system works. So that's all, and thank you for your attention. Thank you.